Okay, hello and welcome back, everybody. Moving on to our section, really subsection of the same, section 5.3, calling it utilizing Green's functions. So in the previous section, we kind of covered the theory behind Green's functions, and we really culminated in this Green's representation theorem, which was a way of finding the solution to really any linear PDE, so long as we know the Green's function of boundary value 0 and all of its boundary correctors. I want to remind you really quick that there's still a typo here. That should be GJ, not GK. So that was where we ended the last section, and we're moving on to utilizing these in the sense that we're actually going to show you some explicit examples of Green's functions that mathematicians have actually discovered over the years rather than keeping things very theoretical. So what we're going to find out by the end of this section is a lot of very specific Green's representation formulas. So you can imagine if I make this very specific by choosing a very specific omega here, choosing a very specific collection of AKs, and then that's about it, because once you choose a collection of AKs and omega, then that kind of defines G and G on the boundary for you. So what are those going to be? Those are really going to be our holy trinity, PDEs. And we're going to start with this definition that's going to help us kind of think about how mathematicians actually discover Green's functions. They actually start with something called a fundamental solution. So a fundamental solution is kind of a generalization of a Green's function where you're independent of a boundary. So a fundamental solution, we denote it by a capital phi, and there it is in the PDE itself. It's a function of two variables, so it's going to be an integral kernel just like Green's functions are. It's going to be a function of two variables. When we plug it into a PDE, we get the delta function out of it. Now, a lot of you may be asking the question, how is this different from a Green's function? And it's different in exactly one way, and the way it's different is that fundamental solutions place no emphasis on the boundary. Or you can also think about them as having a non-existent boundary. So you'll notice there's really no boundary terms in this PDE. All I'm asking is that the fundamental solution, when you plug it into the PDE, equals the delta function. And these are, since they are a generalization of the Green's function, we've just decided to not care about a boundary. It's a little easier to find these objects than the Green's function, because the Green's function is going to care about the boundary. If we get rid of the boundary, then we just make our lives easier. So let's take a quick look at this first example where I'm presenting the fundamental solution of the two-dimensional Laplace's or Poisson's equation. In other words, you can think about it, it's the fundamental solution where the PDE operator is the Laplacian. And in two dimensions, what does this look like? It looks like a logarithm of a square root of, differences between our variables and their conjugates. So if x and z are conjugates, conjugate variables, and w and y are conjugate variables, then basically what is this? This is 1 over 2 pi log of the magnitude of, call it x minus z as vectors, more or less, if x is the vector xy and z is the vector zw. So we're really looking at the magnitude of the difference of the two of them and then the logarithm of that. That's going to be our fundamental solution in 2 dimensions for the Laplace operator. And to prove this is actually no easy feat. So I'm going to go through the proof. I don't need you to pay too much attention to it. This is really a proof that you would see probably your first year of graduate school. It's kind of a second semester real analysis topic to actually prove that this is the case. Let's actually go through it and see what that would look like. If this interests you, then maybe you should think about math grad school. So we're going to note in 2 dimensions that the Laplacian is just the sum of the second derivative squared. And what we're going to try to do is show that the Laplacian of this fundamental solution, or whatever I'm calling this function, Laplacian of this function with the logarithm style, has the property that it's equal to the 2-dimensional delta function. Let's recall really quick that the 2-dimensional delta function is a product of 1-dimensional delta functions. So that's what I'm looking for. I would like to show that this is a true statement, which means I have to pretend like it's not true for now. And what we're going to note is that if you compute a derivative in the xy variable or a derivative in the zw variable, just by the construction of phi, just by this construction right here, you'll notice that it's invariant if I swap x and z and y and w around, which means that actually the Laplacian in either of the two variables is the same. And you could calculate out that it doesn't matter how the Laplacian exists. This is actually always going to be equal to 0 at the specific places where x is not equal to z and y is not equal to w. What you get away with then is we're going to try to show that this object is the delta function, right? So we're going to act it against the function f and hope that it has the sifting property of the delta function. What we can do is, instead of acting that function against f over all of R2, we can actually just act on f over some tiny range the ball centered at xy of radius epsilon. That's what's going on there. So instead of acting it over R2, I'm going to restrict my domain to that ball because that's really the only region in which this computation is non-zero. So certainly I can omit the rest of the integral because it's just going to integrate to 0 everywhere else. So what happens when we make the assumption that we're only integrating over that tiny ball centered at xy? What we can do is we can use Green's identity, and this is actually where the name Green's theorem came from, or Green's functions came from, is that he was really working on this problem in higher dimensions as well. But he was working on this particular problem and tried to prove a lot of these things. And so he got away with his identity here, where when you're integrating a Laplacian against another function over some volume, what you can get away with is translating that entire integral to actually an outward unit normal derivative. That's the outward unit normal derivative, directional derivative of phi, integrated around the boundary. So Green's identity says you can trade Laplacian for the outward unit normal derivative integrated over the boundary. But the price you pay is actually 2 copies of this outward unit normal derivative. So there's a minus sign in the integral. There's really this entire integral term minus this entire integral term. And if you jump back to your calculus 3, you probably did cover this Green's identity in calculus 3. You maybe wrote it a little bit different because in lower dimensions it can look a little bit different. But more or less this is Green's identity. And it just means that instead of integrating over an entire volume of a ball, you can integrate over the boundary. But the price you pay is you now have 2 terms instead of 1. And they both take that form. What we're going to get out of this is we're still going to recover 0 on one of these 2 terms. One of these 2 terms will still be 0, but the other term will actually extract f of xy, which is the sifting property of the delta function, which proves that our original function was actually the delta function. Now we do have to prove this. We haven't proven this yet. We're going to see why it's the case very soon. So what we're going to do is we're going to compute actually this term, this outward unit normal derivative of phi. And when we do that, we get the following. We get 1 over 2 pi and then the square root. Makes a lot of sense, what you would expect if you took a derivative of that function with a log and a square root. And if you restrict this to the boundary of the ball itself, this magnitude just becomes the size of the ball, the radius of the ball, so it just becomes epsilon, which is super useful. And then the 1 over 2 pi, what we get here is 1 over 2 pi epsilon. What do you know? That's exactly the reciprocal of the circumference of the 2-dimensional circle we're integrating over. So in fact, this term here, this entire term, becomes the average value over the ball. So that entire term becomes average value over the ball just by the nature of how phi was constructed. Well, if it's the average value of the ball here, then you write it as the average value of the ball. And the mean value theorem of continuous functions says the average value, if I let epsilon tend to 0, will just be evaluation at the center. So that's really where we're recovering the sifting property, is just the fact that we've constructed this logarithm in such a way that when we take this outward unit normal derivative of it and evaluate on the boundary, we get exactly an average value. So that's really where the construction came from. We can see that the second term in blue from earlier, well, I guess it's inverted blue, so it's probably some form of orange. So this other term goes to 0 just because every function here is a bounded function. That's a bounded function. It's just a logarithm around the boundary. And then this is a bounded function because we just assume that f is continuous. We're working in the space of test functions, you'll recall from section 5.2. So that's going to be continuous everywhere, so that's also bounded. They're both bounded. You're going to let the size of the ball tend to 0, which means that the overall integral has to go to 0 as well. So what we get out of this is that we get this average value integral that ended up as f of xy, and we have this bounded integral over a vanishingly small area that's going to tend to 0. So we just end up with f of xy as the output of this operation, which is exactly the definition of the 2-dimensional Dirac delta function. So that's how you go a proof of one of those. Like I said, if you're really interested, you should think about taking 2 semesters of real analysis. That tends to be the sort of work you go through in those sorts of courses. Otherwise, you can just take it for granted that that's the fundamental solution. And in fact, we can have a fundamental solution for the Laplace equation in higher dimensions as well. So that's what this proposition gives, is it just provides you with the fundamental solution in 1 dimension, 2 dimensions. That's the one we just saw with the logarithm, and greater than or equal to 3 dimensions. And what we're going to get here is in fact, you'll notice that if I had plugged d equals 1 in here, this does actually reduce to the 1-dimensional case. So it's really the 2-dimensional case. It's the only special one here. But what this allows us to do is find the Green's function for the Laplace's or Poisson's equation in very special situations. Now I've got a proof of this as well, but one of them is saved as the exercises, and then the one-dimensional case is pretty easy to prove. But I won't go through that here. Instead, I'm going to move ahead to the Green's representation theorem for the Laplace's or Poisson's equation on the unit ball. So what I've done is I've restricted our domain to a very, very specific domain. So I'm saying omega is the unit ball. And when you read this theorem, just remind yourself this theorem is only valid for the unit ball. You cannot apply this theorem for any other sorts of domains. You have to find a brand new Green's theorem, right? Because the Green's theorem, or the Green's representation, is intimately tied to the shape of the domain itself. But what we have here, we do actually have a Green's representation theorem, because what this gives us is a Green's function, which that is the fundamental solution I just covered. And this is a version of the fundamental solution. So what's happened to this version is that it's been that the y term was multiplied by the magnitude of x, and the x term was multiplied by its inverse. So it's just a slight skewing of the fundamental solution. You take one minus the other. That gives you the true Green's theorem of boundary value, or the Green's function of boundary value 0, which is what you need for a Green's representation theorem. Furthermore, you can actually construct the 0th Green's boundary corrector just by taking an outward unit normal of the earlier Green's function. This is not always true. This just happens to be true for the Laplace equation. Of course, it happens to be true because of Green's identities, as we kind of already saw. There's this intimate relationship between the outward unit normal and the integration over all space. So that's where you can get this boundary corrector, and you can calculate it out, and it just takes the following form. That's 1 minus the magnitude of x squared over your dimension times the total volume of the unit ball in your dimension. Then you multiply that by x minus y in magnitude to the negative dimension power. So that's just going to be the 0th boundary corrector. And then you immediately recover a representation theorem from this, as in the previous section. And just like in the previous section, the representation theorem is the Green's function with boundary value 0 against the right-hand side of your PDE, plus that's integrated over, the original one's integrated over all of the domain. Second one is the Green's boundary corrector, which I've just written in its outward unit normal form, against the boundary value of the PDE, and that's integrated over the boundary. So just keep in mind, you integrate over a volume, and you integrate over a boundary for every Green's representation theorem you see. Now, we should actually see this in action. I'm not going to cover the proof, but we are going to see this in action, where we solve Poisson's equation in one dimension. Now, it might feel a little bit weird to decide to solve it in one dimension. The reason I decided to go to one dimension here instead of 2 or higher is that you can actually compute the integrals in one dimension. In higher dimensions, it's actually quite tricky to compute the integrals explicitly. So I'd like to do it in one dimension just so you can see that the Green's representation theorem actually works for you. And moreover, we actually know how to solve the following Poisson's equation in one dimension just by our calculus knowledge as well. So we're gonna compare our calculus knowledge solution against the Green's function solution. So I'm going to draw that line at the bottom so we know we have a kind of 2 solutions that we're comparing to each other. Let's just say I want to solve this one-dimensional differential equation. It's not an ODE, or it's not a PDE, it's an ODE. And of course, the Poisson's equation in one dimension, delta, capital delta Laplacian, would just be the second derivative. So we'll say the second derivative is equal to 12x squared plus 2. Let's say that on one side of the boundary, which will be -1, we're equal to 0, and on the other side of the boundary, which will be 1, we're equal to 1. So this is just a second order differential equation boundary value problem. It's way easier to compute than other ones because since there's only one term with phi in it, we just integrate the right-hand side twice. So we're going to integrate the right-hand side twice, and we get x to the 4th plus x squared plus c1x plus c2, and we just need to find these to meet boundary conditions. And the way we do that is we just plug -1 in for phi. We see that we get 2 minus c1 plus c2 is 0. We plug 1 in for phi. We see that we get 2 plus c1 plus c2 is 1. Rearranging those and solving for c1, c2, we get 1/2 for c1, -3/2 for c2. Okay, so what that means is that plugging in 1/2 for c1 and -3/2 for c2, we recover the following solution to the second order ODE. It's just a polynomial. But let's see if we can get Green's representation theorem to give us this solution as well. So in Green's representation theorem, if we restrict ourselves to one dimension, we look at the fundamental solution of the Laplacian in one dimension. It looks like 1/2 absolute value x minus y, which means that the Green's function of boundary value 0 is recall, it's the fundamental solution minus the fundamental solution where the x variable has been multiplied by 1 over its magnitude and the y variable has been multiplied by its magnitude. I'm going to scroll back up to theorem 5.3.8 so that you can see that again, right? So it's a fundamental solution minus the fundamental solution where the y variable is scaled by the magnitude and the x variable is scaled by 1 over its magnitude. So that's what we have here for the Green's function of boundary value 0. And then let's recall that the 0th Green's boundary corrector is just the outward unit normal derivative. What is the outward unit normal of this interval, -1 to 1? Well, it's just that direction, which is negative partial x or positive partial x. So the outward unit normal here is just a derivative in the x direction. I've calculated it up to some, deciding if my negatives cancel with some terms there. So depending on the negative or positive partial, I've simplified this a little bit, and we get the following as our outward unit normal, 1 minus x squared over 2, and the absolute value of x minus y inverse. And then I can just write out my Green's representation theorem, where I'm using this is f of x, this and this together form g of x, because g of x is only a function on the boundary itself. So the boundary here is just 2 points. It's just a function on 2 inputs. So I'm plugging the right-hand side of my original equation in for f. This is really me plugging in the right-hand side of g, the g function. I'm just evaluating at the 2 points. And this is the Green's representation theorem. Now, this may not look like it, but this is a quote-unquote boundary integral in one dimension. So the boundary of any one-dimensional interval is just it's endpoints. So the integral is just the sum of the 2 endpoints. It's the sum of the upper one minus the sum of the lower one. So that's what your boundary integral looks like in one dimension. And then the volume integral is of course this one, which occurs against the actual Green's function. And all we have to do is actually compute both of these. This one's not very hard to compute at all. You just evaluate these numbers in for y, right there, and right there, there. Subtract one from the other. So that'll turn out to be this term here. So that's not too terribly important. Actually, integrating this is a little bit tricky, because you actually have to break up your integral to when x is negative or when x is positive because of these darn absolute values of x. It's not the end of the world. This is why we did some practice with calculating integral transforms. So we're actually computing the integral transform here. When you go through all of that work of computing that lovely integral transform, what you end up getting, and adding it to this term at the end, what you end up getting is x to the 4th plus x squared plus 1/2 x minus 3/2. And what do you know? That's exactly what we had recovered directly. That's technically only true for negative x's, and so you can repeat the procedure for positive x's, and believe it or not, you do recover the exact same formula. And so this Green's theorem, or this Green's representation theorem for the Laplacian really does work. That was just the one-dimensional situation, but you can compare it to the one-dimensional solution we got. It really does work for Laplace's or Poisson's equation on the unit ball. So that's really nice to see. See a little bit of verification when you compare it to the answer that you get directly. We can then move ahead to the rest of the Holy Trinity. That's kind of what we're going to be covering in this section, is all of the Holy Trinity PDEs. So we covered the Laplace's equation. We found a Green's function specific to the unit ball. You can find Green's functions in some very specific domains, other domains as well, but you can look those up if you want to see them. We're going to move on to the heat equation, which also has a fundamental solution. And let's recall that the fundamental solution is just the Green's function, except you don't have any sort of boundary condition on it. The fundamental solution here is, that's the Heaviside step function, or the unit step function. You probably recall from some Laplace transforms. It's just a function that's equal to 1 when t is greater than s, or equal to 0 when t is less than s. And then it multiplies by the Gaussian, but in the denominator of the Gaussian you have t minus s, and then actually out front you have a corrective term that depends on the space divided by 2. The power of the dimension divided by 2 is the corrector term for this. This is really the variance of your normal distribution, and so you have some corrector terms coming out front to meet that variance. So that's a fundamental solution of the heat equation. We really can't get into the proofs on a lot of these in this chapter. We're getting to a point in this book where the math gets really, really difficult. So if you're interested in the math at a deeper level, once again, head to graduate school. Otherwise, you can go ahead and check out section 2.3 of this book, Evans PDEs. It's a very common graduate text in PDEs. And you can see that's only in section 2. So he's got like a 20 chapter book, and on chapter 2 you're already covering kind of what the end of this book covers. We can see the Green's representation theorem for the heat equation as well. So recall this is the fundamental solution, and a fundamental solution and Green's theorem are not the same. So we have to find Green's functions out of the fundamental solution. In this case, we get pretty lucky if we decide to make our domain the positive time multiplied by d-dimensional space, which is kind of the regular way you would set up a heat equation over all of space. So if you let your boundary be time 0 and then you retain all of space, then the Green's boundary solution is actually just the fundamental solution. So you get away with something quite nice on the Green's boundary. And the boundary corrector is also very easy. You just evaluate the fundamental solution at s equals 0. So adding these together, you can get a representation theorem right away, where I've split up my integral just to make it kind of clearer how it's often performed. You kind of perform the spatial integral and the temporal integral in two separate steps here. So there's the spatial term and then the temporal term. You'll notice I went from 0 to t. That's because I included this heavy side because it's only equal to 1 over that range from s going from 0 to t. And then I just decided to truncate the integral there, and I didn't include h in the actual Green's function part of the representation theorem. So in the representation theorem, you just grab this function f, you swap the variables for their conjugates and plug it into the integral transform, and then you also grab this function g and you put it in the boundary corrector term. So there's the Green's representation theorem for the heat equation. And we can actually see an example of this as I've provided here, which I'm calling heat spread through a V6 engine. I wanted to give some sort of a slightly more applicable example here. And what I've done is I've constructed an omega here where it's equal to, there's a really nasty way of describing this set, but you can actually see the picture below. This is the set omega, really all of the gray is omega, which I guess is showing up as white to you. So the kind of the off-white, light grayish is omega here, all of those 6 dots. And those are going to be the cylinders of a V6 engine. And what's going to happen is the engine is going to start out cool, but then I'm going to turn the car engine on, and all those cylinders are going to start firing. So locally, the heat's going to rise extremely quickly within each of those cylinders. And then after a few minutes, I'm going to shut the engine off, and I'm going to watch the heat spread. So let's assume that after 5 minutes, we turn the engine off. So we turn the engine on. These cylinders are running. They're running really hot because there's explosions happening inside of them. And after 5 minutes, I turn the engine off, and then I want to see how the heat spreads. So what I can do is I can set up a heat equation. So let's just say we have a heat equation here, which makes a lot of sense. But I need a forcing term. So this forcing term is going to describe how heat is input to the system. Right? F is going to describe how heat's input to the system. What I'm going to do is I'm going to say F, the forcing term, adds heat at each of these 6 nodes, and exactly on top of each of these 6 nodes. That's what's going on with this term here. But the heat addition, right, because it's a forcing term, shuts off after 5 seconds, and so that's why I can include the Heaviside step function 5 minus t. So it turns into 0 when t is longer than 5 minutes, but within those 5 minutes, we're just going to run constant heat out of each of the cylinders and see how those spread. And then I'm also going to write out an initial condition where the initial condition is also in the shape of the cylinders. Because the idea is it's just air inside the cylinders right away. The moment I start the car engine and some explosions happen in those cylinders, they immediately heat up to something very hot. So I'm going to call those actually hot from the beginning. A millisecond after I actually start the engine, they're going to be hot. So I'm going to call those hot from the beginning and then include that forcing term I was just talking about. And we're going to try to solve this heat equation over technically all of R2. Okay, this means it's an infinitely large engine, but you can make those assumptions in short time periods that the heat doesn't have enough time to spread to the boundary, so you don't really worry about having any specific boundaries there. But this is going to be a heat equation that Green's representation theorem can actually solve, right? So this Green's representation theorem for the heat equation can solve the one that I just set up, where F describes each of the cylinders constantly outputting heat for the first 5 minutes, and G describes that each of them are hot from the beginning. What the solution looks like, all I have to do is grab F and actually plug it in to the representation theorem. And what that looks like is an integral over omega. And then I can just plug G in at the beginning, which is this. And that also just looks like an integral over omega. And then the Heaviside term that was inside of F is going to restrict the time that I integrate from 0 to t. It's actually just going to be 0 to the minimum of time t in that direction here. So really what I have as my solution to the heat equation is this collection of integrals. And unfortunately, there is no closed form solution, but you can actually plug those integrals into a computer and get the computer to give you approximations at every point in time. And so what I've done below is I've computed heat maps of what this solution actually looks like, where I truly did use this formula to calculate this heat map. I was just plugging at each moment in time, choose an x and a y value, approximate the integral, wash, rinse, and repeat. So this is a heat map actually produced by my Green's function, Green's representation theorem, for the heat equation. And what we can see is all 6 cylinders immediately heat up right away. And then after this step is where after this step I stop engine, and then each of the cylinders starts to cool down as well. The heat starts to diffuse away from all of them. So the heat makes its way through the engine as I wait longer and longer after I've turned it on and then shut it off again. You can imagine if you wait long enough, then it kind of returns to where it started, and then the next time you start the engine, the whole process repeats. So this definitely has some real world application where you can represent some very nice scenarios and especially get some very nice photos. But let's move on to the very last case of the Holy Trinity, which is the wave equation. And we're going to do the wave equation on all of space. I don't even cover the fundamental solution of the wave equation. I don't want to. It's really, really hard. You're going to see the Green's representation theorem also really hard for the wave equation on all of space. What do I mean by all of space? We're going to still initialize at time t equals 0, but the spatial terms will just be RD. And if I have some sort of forcing term in my wave equations, I have some initial wave shape, and I have some initial wave velocity, I can actually construct an integral transform solution to these, and they look terrible. They look so bad. So what's going on here? Why do I have so many of these? Well, it depends on the parity of the dimension. Parity, what I mean by that is odd versus even. So if my dimension is odd, that's going to be the top case here. So an odd dimension, my solution to this PDE, which is a fairly simple PDE, but the solution looks so bad. So what do I have to do is I grab D, my odd dimension, I plug it into this thing that's called gamma. We won't worry about it for now. I also plug D in right here. It's going to be a power on t minus s inverse times the partial derivative of time. I'm going to plug T in over here, or D in over here, and then I'm going to repeat on the next line, plug D in there, plug D in here, also another gamma. And then I'm going to repeat on the next line, plug D in here, plug D in here, and also one more gamma. And then I'm going to integrate over my time period, 0 to t, until the present. I'm going to integrate over a boundary of the ball. Well, that feels weird if we're trying to do a Green's function. Normally you integrate over all of space. Why are we on the boundary? This is a weird case when the dimension is odd, that you only end up working on the boundary of balls, but the radius of the balls themselves depends over time. So it's the fact that you're integrating over all of time, that you're integrating boundaries over radius, that technically you're integrating over the entire ball. It's like you can think about at time t equals 0, it's the boundary of that ball, time t equals 1, that ball, 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 that ball. And so that when you're filling up these basically onion shells, right, these nested onions, that you do recover the entire ball. So it looks like you're only integrating over the boundary, when in fact you are actually integrating over the entire ball. It's just not quite clear that that's what's going on. It's the combination of a positive integral in the time direction, as well as a lot of boundaries over and over again, growing boundaries of balls. So that's what's happening in odd dimensions. And then these truly are like the boundary correctors of the Green's function. So this is what the boundary correctors look like in this case. Yeah, I know it's terrible. We're not going to put too much thought into this. And in fact, this gamma, which depends on the dimension d, just looks like a product of all of the odd natural numbers strictly less than d. That's all it is. If you want to see how this is actually computed, you should see theorems 2 and 3 for the odd and even solutions in section 2.4 of Evans PDEs. But honestly, I haven't even spent that much time looking at them. I just kind of take them for granted when I need to use them as well. When d is even, you do see that you do actually integrate over the entire ball over here. So this is the difference between even and odd. And once again, you just plug everything in, you cross your fingers, you get some sort of approximate answer. It's not easy though. It's really not a nice representation formula, but it's better than nothing. I mean, the fact of the matter is that it exists, right? So no matter what f, g, or h I decide to grab, I just plug it in, plug it in, plug it in. I have my solution. Same thing in even dimensions. So it's frustrating that solutions look so ugly, but it's not the end of the world when we have computers to do the integrals for us. I will comment though, there are special cases of restrictions to 1 and 2 dimensions, and in fact even in 3 dimensions, we give all of these formulae special names. And in 1 dimension, it does simplify a lot. So in 1 dimension, this is known as D'Alembert's formula. And you're going to hear this a lot if you study the wave equation in physics. Almost the first time you run across it, you're going to be talking about D'Alembert's formula. So this is good to know. This is the quote unquote wave equation solution. You should leave this course knowing. So D'Alembert's formula is just going to tell you in one spatial dimension, right, x is in r, where to put F, your forcing term, where to put G, your initial wave shape, where to put H, your initial wave velocity. You just plug all of them in. There's the F formula, there's the G formula. Notice it occurs over the boundary. There's the H formula. So you just plug each of them into this formula. It's called D'Alembert's. You will get your answer. It will be the unique solution to the one-dimensional wave equation where your boundary is all of R, or your domain is all of R. In 2 dimensions, I'm going to skip that really quick. In 2 dimensions, it's called Poisson's formula. So you'll notice I've replaced the delta, the Laplacian, with the partial x squared and partial y squared. And then your function is allowed to have 2 inputs. Same. Poisson's formula looks like this. So it looks a little bit uglier. This is like truly direct from the earlier Green's representation theorem, but it doesn't look like the end of the world when you write it in 2 dimensions, because you can factor some terms out. Now I do want to make a very quick note about this 2-dimensional case, and that's that this function g, you'll notice that it has a derivative in both directions taken of it. So there's a very strange property that the initial wave shape, actually the derivative of the initial wave shape, plays a role in 2 and higher dimensions, which is not what you would necessarily expect. Certainly not from 1 dimension, because if I look at D'Alembert's, there's no derivative of the initial wave shape showing up here. So it's a really interesting thing. This concerns regularity if you ever get into regularity. But in higher dimensions, you actually, I think it's just in the even dimensions, actually, you care about the spatial derivative of the initial wave shape. That's just something to note about the 2-dimensional case. We're going to look at one final example, and then we'll be done for the day, because I know it's been quite a long video here. Final example is D'Alembert's formula in action, where if I have a 1-dimensional wave equation, notice there that's x and r, so it's just partial x squared of phi, and I've got a nice little forcing term here, a lot of delta function forcings. By the way, you can force equations with delta functions. You don't have to just use them for representation theorems. Suppose I'm forcing with a nice little summation of delta functions. Got an initial wave shape there, an initial wave velocity there. All I do is I find D'Alembert's formula. Here it is. So I'm just going to plug this term into D'Alembert's. For the F case of D'Alembert's, I'm going to plug this term in the G parts of D'Alembert's, and I'm going to plug this term in the H cases of D'Alembert's, and then I'm going to go ahead and compute those. So to compute all 3 of those integrals is not too bad. I mean, the center integral is not even, this one's not even an integral. It's already been evaluated for me. But the other 2 integrals, this one's not too bad. Integration by parts will get you there. And then this first one, recall the integral of the delta function. It has the sifting property. And in this case, it sifts against, there's a hidden function 1. So we've got a sifting property against the function 1. And what that sifting property against the constant function 1 is going to give you is some heaviside step functions multiplied together. And so you integrate all of that. This sum, of course, just came out here is this sum, and then the integrals were those heaviside step functions. These all combined into the Gaussian here, kind of a shifted Gaussian. And so what we see as our solution as time evolves is the initial wave shape. It has an initial velocity straight to the right, which we can see for a few seconds, until the first delta function forcing shows up. So this is really an impulse forcing that occurs at every second in time. And the delta function impulse force comes through and it shoves that in the wave, comes through again, it shoves that, comes through again, and it just keeps shoving terms into the wave because it's an impulse forcing. It's like you're spiking the wave with a nail, and that'll spread out the wave over time. So that's just like a nice little example to see D'Alembert's in action. But it's been a long video. Sorry for taking so long. I hope it all makes sense. Basically, just think about, we have Green's representation theorems in a lot of very particular cases, the Holy Trinity being kind of some of the most famous. And they give us the ability to find solutions right away, just by grabbing your initial conditions, your forcing terms, and so on, and just plugging them directly into a representation theorem. Anyway, that's all I got. I'll see you in the next class. Bye.